Cat, your friendly chemistry tutor.
Resonance structures. Do you ever wonder if your indoor cat actually likes staying at home all the time? Or maybe, deep down, she desires to be free and roam the streets or sit on the grass and eat bugs for fun? I guess we'll never know. Electrons are similar to this. Localized electrons, such as sigma electrons, in single bonds, and lone pair electrons that are 1, not next to a pi bond, 2, not next to an empty p orbital, and 3 are pointing away from the pi system, just like this lone pair, that is horizontal in comparison to the pi system direction, that is vertical. These are all likely to stay in one place and don't really move or resonate around the molecule. They are the indoor cats who are stuck at home. Delocalized electrons, like pi electrons in double or triple bonds, and lone pair electrons that 1 are next to a pi bond, 2 are next to an empty p orbital, and 3 are inline or parallel to the pi system, just like this lone pair that is vertical in comparison to the pi system direction that is also vertical. These are all likely to move or resonate from atom to atom. They are the outdoor cats who go out and explore. A resonance structure represents the delocalization of electrons within a molecule. These delocalized electrons resonate around the molecule as shown here until they find a spot that results in the most stable structure, because just like human beings, molecules also want stability in their lives. Before you learn how to draw resonance structures, there's a few rules that you must follow. You certainly won't go to jail if you break these rules, but you might fail your chemistry exam. Just letting you know. Rule number 1. Use curved arrows to show electron movement. The arrow starts at the electrons, which is either a lone pair or the pi electrons in a double or triple bond. And the arrow ends where those electrons go to form a new bond or lone pair. You draw the arrows on the structure that you're gonna change, just like I did here on the left, and then show the results of that change on the next structure, as seen here on the right. Rule number 2. Only electrons move, not atoms. Which electrons move? Just like we discussed earlier, only the lone electrons that 1 are next to a pi bond, 2 are next to an empty p orbital, and 3 are pointing inline or parallel to the pi system, and pi electrons in double or triple bonds. These are all highlighted in red here. Don't ever break a single bond. That will piss your teacher off. You can add electrons to a single bond to make it a double or triple bond, but you cannot take electrons away from it. Rule number 3. Maintain the same number of total electrons. You are just redistributing them, not adding or removing. Rule number 4. Place formal charges correctly. If electrons move away from an atom, it becomes more positive, just like how this oxygen went from -1 to 0. If electrons move towards an atom, it becomes more negative, just like how this carbon went from 0 to -1. Calculate the formal charge each time to make sure. Which brings me to rule number 5. Prioritize stability. The best resonance structures are the most stable, with minimized formal charges. And when charges are present, put the negative charges on more electronegative atoms and positive charges on less electronegative atoms. In this example, the resonance structure on the left is more stable because although we see a formal charge of -1, it's on the oxygen that is more electronegative than the carbon. Last but not least, rule number 6. Never exceed the octet for atoms. Since you are moving electrons throughout the molecule, make sure that the atoms don't have an overload of electrons by exceeding their octet, or else they'll feel super negative and won't speak to you again. Side note, hydrogen only likes 2 electrons, also known as having a duet. The best and most stable resonance structure contributes the most to the real or ideal electron distribution in the molecule. When determining the best structure, you want to prioritize the following things here that we have already discussed in our rules. Now take a deep breath and try it out yourself. Use arrows to draw 2 additional resonance structures for the molecule below known as furan, and then rank all the structures from best to worst. The best structure contributes the most to the electron distribution of the molecule, and the worst structure contributes the least. Be sure to indicate formal charges as you go. Pause the video and return when you are ready. Welcome back. Let's get into it. It's best to start with the delocalized lone electrons on oxygen, moving them over here, and then moving this single bond over there. This will lead to a structure that looks like this, with a bond formed over there and 2 electrons on carbon. This gives carbon a formal charge of -1, and it gives this oxygen a formal charge of +1. This is already a red flag. I hope you understand that. Now, I can go ahead and move these 2 electrons on carbon over here to form a bond. This will lead to a structure that looks like this. We already have the bond from earlier. Now we have a new bond formed between this carbon and the adjacent carbon, which will eliminate that positive charge on that carbon. We still have a positive charge on oxygen from earlier. So, if I wanted to rank all of these structures, I would rank this as number 1 because it has minimized formal charges, and even though there is a positive charge, it's actually on the carbon, which is the less electronegative atom. I would rank this one second because although there are formal charges, it is on the oxygen, but it's not as worse as the next one. This is obviously going to be ranked last because there is a positive formal charge on oxygen, but there's also a negative formal charge on carbon, which is less electronegative. I hope you understand all of this, and I hope this helps you. Thanks for watching. You can find a full 7-page worksheet on resonance structures that has more practice problems, exercises, and a full answer key on my Etsy, Payhip, or Gumroad page. Additionally, if you have any questions, feel free to email me at chemcat786@gmail.com. Don't forget to like and subscribe to support my content.